Hi guys, I've not done a video in quite a while. I have actually changed jobs and that has taken up, well, 100% of my time. So it's been a couple of really busy couple of weeks. I have however gotten to a point where we've upgraded, or I've actually got the power supplies first and the first stage to actually work as expected. I have well, I will be marking my previous videos as incorrect. I am leaving them online though, so hopefully someone else can learn from my mistakes. But I've now come up with a better design and more standardized design. I don't know what I was thinking the first time. It's kind of standard. I knew this. I have no idea why I completely deviated. It's one of those things where if you get your head stuck in something, it's just hard to extract yourself, and you need to sometimes just take a break and figure what's happening. Anyway, I'll take you through the circuit diagrams. I've made a couple of changes to the second stage as well, which I'll take you guys through, and I'm thinking of making a bit of change to the third stage as well, actually. But let's get going, and I'll quickly show you just what we have so far. So this is the updated working version of the design. So you'll see it's a two-stage board as the original design. I was originally planning to put standoffs from the bottom board to the top board. I might still do that, but I'm battling to find standoffs long enough, and these guys nicely crimped and bolted down actually work really nice. So I might end up going with that design in the end. So down the bottom there you can see we have where the transformer connects into, right between those, that's the common, and so minus 12 common and plus 12, and I'll get to talk about that in a moment, through to the inrush current limiting board. Through that, going back, there's our relay to actually short it out once our caps are loaded, and then over on this side you'll see that goes up to the next stage, which we'll talk about in theory for a bit. This is here's our bulk capacitance board. You'll see here that I've changed from the 18 by 18 transformer to a 12 by 12, and I'm still expecting 34 and 17 volt on the output. Now this is something that vexed me for a couple of moments until I remembered about RMS voltage and not RMS and peak to peak effectively. The difference being that when you vote, so I worked out 36 volt and 18 volt on each side, forgetting completely that there's a net gain in your capacitor bank, because it charges up and effectively stays there, which is one of the big reasons why you have a cap bank there. So the formula for that is obviously your transformer voltage multiplied by the square root of 2. Which is roughly 1.41, 414, I think, which obviously gives you that almost almost a 50% gain on top of your input voltage. Now I need to still do some testing on that, and I'll do that once I get to actually load down the transformer. But you know, that is it'll rise up to that at no load. Once you start applying load, that's obviously going to come down. My concern is that the LT3080 that I'm wanting to use for the next stage has a maximum input voltage of 36 volts, and I don't want to blow that. So I might end up having a power supply where the output voltage is not going to quite reach 30 volt under load. But right now we are pushing 34 volt into our next stage. So just to be clear, the formula for that is your input voltage times the square root of 2, and you have to minus any voltage drop across your rectifier diode, and that is normally 2 times 0.7, or where 0.7 is the drop voltage of your particular diode. I've also replaced the diodes that are specifically used in this design. These guys now can manage 10 amp each, so they're quite a bit beefier, and I'm hoping everything should be fine. So just to show you the quick layout on that, there is just the layout. So what we're seeing is there's our common for our transformer. This will be our positive 12 volt rail, our negative 12 volt rail. I'm taking the common and I'm tying that down to the bottom pad at the bottom, or connector at the bottom. And so, but I am then raising my, so if, let's just think about this. So there's our negative rail coming in through the rectifier diodes, our other one through rectifier diodes, and the outputs of that we are sending to our inrush current limiting. So we'll look at the inrush current limiting board now. Anyway, it comes back and then feeds through our high voltage rail there. Our low voltage one comes out on this side, and our common comes through in the ground. So what we're effectively doing is we are grounding our negative rail. This will have the effect that we'll have 17 volt coming out in the low voltage version, or low voltage connector, and 34 volt in our top one, which is lower than our 36 volt max, but higher than our dropout voltage of our 3080s. So theoretically everything should work fine. Let's look at our inrush current limiting board. The inrush current limiting is as you'd expect, simply a set of resistors. I've paralleled up 10 470 ohm resistors. So paralleling them up effectively gives us back 470 ohm, 3 watt each, so we have quite a bit of power dissipation. And the reason for that is while these resistors are engaged, we're limiting the inrush current to 1.5 amp, or less than 1.5 amp. So that should be fine for our diodes to deal with. Now in this case, these particular diodes I've replaced it with now should be completely fine. You shouldn't actually need the inrush current limiting, but I'm putting it in for good measure anyway, and I've designed the board and it's already working. So it'll come in, rush through these resistors, fill up our capacitor bank. Once the capacitor bank is filled, roughly 1.5 seconds after you've applied the power, we can turn on our relay, which effectively shorts out the resistors, and we then have full power applied to our further stages in our power supply, right? Or full current, which then would allow me to actually reach the 3 amp output current that I need. And then there's our off-board connector, just to manage this all the way from a microcontroller. Right, quick look at the layout. You've seen this before. This has not changed. So effectively just big beefy resistors, 10 of them, double side loaded. Our relay sitting over there, and our off-board connector that filters through all the various stages of our power supply. So this is effectively our data bus. Okay, then let's have a look at so this is where I said I've made some significant changes to the second stage, or the second stage of our power supply, the actual regulating board of our power supply. And I wanted to take you through this in more detail. So what I've implemented here is I've added a relay to this board, and what you'll see I'm doing is this relay is a latching relay, right? So we don't need power to keep it engaged. The higher voltage you apply to a linear regulator, the more power it has to dissipate when you're drawing a lot of current at lower voltages. So the idea being that if you are below, let's say 15 volt, you will actually be using the 17 volt rail, so you'll only have to dissipate a little bit of power. Once you go over a certain threshold, and I'll still need to figure out what the actual thresholds are, the relay will flip over to use the high voltage rail, which then allows you to manage your power dissipation better. Now I am putting an enormous, or I'm planning to put an enormous heatsink into this thing, but I do want to focus at least a little bit on the efficiency of the design as well. Actually, I've also added a 12 volt regulator in this case. Now, I'm not adding a 12 volt rail on the output to the front. The 12 volt is driven by a very small, another linear 7812, so just a standard little half amp 12 volt regulator. And the idea being that this will drive our fan. The fan will be, the temperature of the heating near the regulators will be monitored from with a temperature sensor, and will be turning on the fan gently as we go, to keep the noise levels down, of course. I'm still using the op amps to drive the voltage directly to the power supply, to the linear regulators, the 3080s, but there's obviously the digital path from our shunt and power monitors, which I've covered before. One additional thing I have added to this design as well are these two off-board connectors. And effectively the idea with them is that you could put a stock standard 10-turn pot onto those and manually change your voltage. So we could actually, the idea being that this is a modular design, and if you didn't need a full digital power supply, you could opt out to leave out your digital to analog converters and a lot of the digital circuitry, put two 10-turn pots on there and have a fully functional power supply. Obviously you will lose the digital watchdog type stuff, so if anything goes wrong in your op amp circuit, there's no microcontroller to kick in and take over. You won't be able to monitor your power, you won't be able to do all the other functionality that I'm planning for this design. But at least you'll have a functional power supply, right? So that could be a base version, which would allow quite a bit of functionality on its own as well. It'll still have 0 to 3 amp current limiting, 0 to 30 volt output power, and you can also still add in the other two phases, so you would still have a 5 volt and a 3.3 volt static output, but you will lose things like your dynamic power management, anything the microcontroller is responsible for right now. That's the design to date. Obviously still a bit of work to do. I do need to swap out my transformer. So this is my 18 volt by 18 volt transformer, which I originally planned before my brain woke up. I do need to replace this with an equivalent 12 volt version to make up for the gain in our capacitor bulk capacitance stage of the design. Okay. That's the update I want to give you quickly. I said it was going to be a short video. Give me your feedback. I'd like to hear more from you guys. If you have any better suggestions, thoughts, ideas, leave them in the comments down below. If you like this video, subscribe. Thanks to all the guys that have subscribed. Tell your friends, tell your family, give it a thumbs up, and see you in the next one.